Hi everyone, welcome to the last video of this series of quick guide videos for the chapter on electrolysis. Now in this video, right, we are going to take a look at the simple cell, right? So in the previous two videos, we actually explored more on the electrolytic cell, whereby we spoke about the process of electrolysis, right? How the battery actually generates the electricity that's needed for the reaction to happen, right? Then we spoke about what happens if the electrodes are inert and what happens if they are reactive, and also what can be the possible observations if we were to change the electrolyte, be it in terms of molten or aqueous state, or be it in terms of diluted or concentrated state, right? So that's what we spoke about. And of course, we have this acronym over here, NOx RedCat, which will be the same throughout, be it for electrolytic cell or simple cell, whereby anode is where oxidation happens and cathode is where reduction happens. So today we are going to take a closer look at the simple cell, right? So the simple cell looks very, very different from an electrolytic cell, mainly because of the component that's over here, right? There's no longer a battery, and this time around you have a voltmeter over there. But I just want to caution everyone to note that it need not be a voltmeter here. It can be any form of electrical appliances, right? Be it in terms of a light bulb, right? For example, an ammeter, etc. It doesn't really matter. So just take note that in this case, for simplicity, we use a voltmeter so that we can measure the voltage that's being generated. So how does a simple cell works? Now the key thing to note in a simple cell is that this time around you must use two pieces of metals. You can no longer use a graphite or a carbon electrode. You have to use two different pieces of metals. And what happens is that when you place them in an electrolyte, which usually tends to be, so this is the electrolyte, and usually we use the electrolyte of sulfuric acid, right? So what it does is it actually allows one of the metals to go through a reaction and thereby generates an electricity. So the idea of simple cell is that you make use of chemical reactions to generate electricity, or to generate electrical energy, to convert into electrical energy. So this is actually how most batteries work, right? So most of the batteries that we have around us are actually simple cells, right? They make use of reactions that happen within them, and through that we are actually able to get electricity to power our things like a phone or remote control. So what do you need to note for a simple cell? Now in a simple cell, what you must take note of is you must be able to identify the difference in terms of these two metals based on their reactivity. Okay, so just a quick one, we have learned in the earlier chapter in metals about the metal reactivity series, right? So these are the ones that you have come across. Okay, the idea of a simple cell is that you have to choose two metals that are different in terms of their reactivity, and the greater the difference is, the better it is at generating electricity. Okay, so for instance, for example, right, let's say that this metal X and metal Y, I'm just going to change them into actual metals. So let's say that one of them is zinc, for example, over here, and the other one is actually copper. Based on our understanding, we know that zinc is a lot more reactive than copper, right? Because of this gap in reactivity, right, it means that zinc can actually react in this case, and in this setup, it will generate a certain amount of voltage. So what happens is that this zinc that you see over here will actually go through a reaction. The metal over here will actually go through a reaction to form zinc ions. Okay, remember that half equation all needs electrons. So this zinc metal will go through reaction, and when it does so, it actually generates electrons that comes out from the electrode and move towards the other side and enters through the copper metal. Right, so what happens now is that there's a flow of electrons, and in order to keep the circuit closed, something within this electrolyte must be able to accept the electrons that's coming down, right? So because copper by itself, this metal copper, can't do anything with these electrons. You don't see copper taking electron to give you Cu minus, for example. This doesn't happen. So what must happen is that within this electrolyte, there must be certain ions, and true enough, there are ions such as H plus over here, right? The H plus ions will then move towards this component because H plus ions are generally interested to taking electrons to go through reduction. So what happens is that the H plus ions here will go through a reduction process by adding in 2 electrons to form hydrogen gas. So overall, what exactly happens in this entire setup? First and foremost, zinc goes through a reaction, right? It reacted because it's more reactive than copper, and they are being established in this setup. Secondly, at the other side, hydrogen ions are the one receiving electrons going through reduction to form hydrogen gas. So in terms of observation, what will you see? We'll definitely see a lot of effervescence at this electrode because hydrogen is a gas, right? As it comes out, you form a lot of effervescence. But on these other electrodes over here, what will happen? Because the zinc is constantly reacting to form zinc ion, we'll notice that this electrode will start to get smaller and smaller. And eventually, it will just be totally used up. Right? So what happens at this electrode over here, right, should become smaller in size, right? Because of the reaction that's happening, so it uses up all the metals that's present over there. Okay, that's actually how a battery works, right? So that's why a battery can have a shelf life whereby it will eventually be used up, right? Because if all the reactants are being used up, then that's it. Now, what is the importance of knowing the reactivity? Because the greater the reactivity, the more voltage can be generated in this case. So for instance, let me change this entire setup. Let's say that I change this metal over here. Instead of copper, let me say I'll use gold, for example, right? This time around, the difference is no longer between zinc and copper, but it's actually between zinc and gold, right? So if you compare the two, definitely you see a big jump in terms of additional difference in reactivity, and this will actually generate more voltage that will comes out, right, when you use a greater difference. So what this means is that if the first one actually gives you 1.5 volt, second one might give you 2.0 volt, for instance, right? So this is actually what you can use to understand how a simple cell generates the voltage or the potential difference in this case. Now, what if instead of using zinc with something that's below it, right, we use zinc with something that's above it by keeping the entire system as is. So let's say I change this into magnesium, for example. Right, now this time around, because if you compare them, magnesium and zinc, this is the difference, right? But because magnesium now is the more reactive one, it doesn't make sense to say that, oh, the electrons are leaving out from the zinc anymore. So this entire example will not hold, right? So if we are really having zinc and magnesium as a form of example, right? So let me just erase everything. Okay, so imagine you have this entire setup whereby you have magnesium and you have zinc, right? This time around, because magnesium is a lot more reactive, what will happen is that the electrons will start to move in the opposite direction, right, from magnesium towards the zinc, and therefore the one that's really reacting in this case will be the magnesium, right? Magnesium solid will still through oxidation, and this all depends on which one is more reactive, right? The one that's more reactive will allow electrons to be released out because the metal went through oxidation. And now when the electrons come down over here, okay, likewise H plus ions will start to move over here to react, and you have your reaction between hydrogen ions as well as the electrons to form hydrogen gas. So this time what will happen is that you start to see effervescence over here, and this electrode will actually become smaller and smaller and smaller in size. Okay, and when this thing happens, something interesting takes place. Just now I mentioned to you that if I were to compare between zinc and copper, I might get a 1.5 volt difference. If I compare zinc and gold, I might get a 2.0 volt difference. Now, when I start to compare backwards from zinc towards magnesium, right? So if I compare from zinc towards magnesium over here, what you realize that the reading here will actually turn as negative. So it might be negative, say 1.2 volts. Now, why is that the case? It actually has to do with how the voltmeter is being set up, right? Because if the current were to flow in the opposite way compared to just now, right? So just now it looks, so let me just undo everything. Right, so just now when the setup was like this, okay, with the current flow in this manner, if we get a positive reading in the voltmeter, if the current were to reverse, right? When the current reverse, the entire thing actually, the symbol will actually change. Okay, so once the current starts to reverse like what we have now, because magnesium is more reactive, then you will get a negative reading for a voltmeter. Okay, so of course, some of you might be thinking, so is it possible for me to get 0 voltmeter reading? So the question to you is that, Will that be possible? If that's the case, what would be your two metals? Alright, and with that, we've come to the end of the chapter on electrolysis. These are just 3 short videos to give you the big idea about what the chapter is about. And that's all. Thank you.